Good afternoon, students. My name is Ravi Ranjan Kumar, and I welcome you all to this session. Okay, this week we were revising mechanical properties of matter, and we already covered viscosity and surface tension, and this would be the final lecture. And in this lecture, we will be covering elasticity. Okay, so without losing any further time, let's share our screen. Okay, so let me start here. And, okay, so here we go. So today's topic is elasticity. I hope I am visible to all of you. So today's topic here is elasticity. Okay, so as we all understand that elasticity is property of material by the virtue of which it tries to regain its shape when external deforming force is removed. Okay, and let's try to look the microscopic reason for elasticity. Okay, so when we will be looking at potential energy versus separation graph of molecules, this graph looks something like this. Okay, so clearly you can see, let's say for example, this is R is equal to R naught. So here you can see that du by dr is equal to 0. So that is an equilibrium position. And also you must realize that this is a minima. That means d2u by dr square is basically a positive quantity, or you can say df by dr here would be negative quantity. So this is a stable equilibrium. Okay, so that means when molecules are disturbed from equilibrium separation, a restoring force starts acting, which tries to get the molecule at stable equilibrium position. Okay, like for example, if we displace slightly, let's say over here, so when we will be looking at the slope of this graph, okay, so here slope is negative. Here you can say the slope of this graph is basically positive, so df by dr is negative over here. So clearly we can say that a restoring force will be acting in either direction. You can say either direction you displace, the restoring force will be directed toward the equilibrium position. Okay, so this is the microscopic reason for elasticity. And you should also observe that the non-symmetrical nature of this graph. For example, if we separate the molecule, okay, so the material will be behaving differently when under elongative stress, and if it will behave differently if it is under compressive stress. But for if the displacement or change is small, you can near this point you can realize the symmetric nature of this graph. But if the deformation is large, okay, so it behaves unsymmetrically. Okay, so this was microscopic reason for elasticity. And the next thing we should be covering is, like, in order to study the behavior of elasticity of a material, okay, we use certain physical parameters in order to study that, and those parameters are basically stress and strain. Okay, stress I will symbolize simply at sigma, and strain I will symbolize simply as epsilon. Okay, so this we can define in three different ways. Okay, so first one is known as longitudinal stress or strain, you can say. And the second one is nothing but shear stress or strain. And third one is, you can say, volume stress or bulk stress or strain, you can say volume or bulk. Okay, so longitudinal stress is defined as, let's say, sigma L would be perpendicular force upon area, and uh, this strain would be defined as, longitudinal strain would be change in length by L. Let's say, for example, we have a wire, okay, and I am trying to stretch it by exerting some external force from both sides. Okay, so its initial length is, let's say, L, and under the stretching, let's say, it will stretch by delta L. Okay, so you must realize that how we are defining this strain over here, that is change in length upon the original length, so that is delta L by L. And you should also realize, so this change in length will cause any element of this to experience some stress over here. There would be some restoring force. Let's say this element will experience F force, and let's say this is X, and this element is dx. So this would be F, and this is F plus df, etc. So this element, you can see, is under elongative stress over here. So now you should realize, okay, that this is how we are defining the uh, longitudinal stress. Okay, and that is perpendicular force upon area. A would be the area of cross section over here, and this force here, as we can see, it is in perpendicular direction. So this is how we define longitudinal stress and strain. Whereas the shear stress and strain, we can define, shear stress would be parallel force on a surface upon the area of the surface, and shear strain would be defined as something called delta X by L. And let's try to understand it using a diagram. So let's say this is a surface, and for example, say we have a cube here, okay, of say its length is L over here, and its area of the topmost surface is A, and let's say it is fixed at this edge. So if we apply some force parallel to the surface, external force parallel to the surface, so it will experience, okay, due to this, what will happen is, it will cause the deformation in this body, and the shape of this body will become something like this. So let's say it has moved by some delta X, or you can also say like this angle is theta, so it is having, okay, this much strain, that is shear strain, and that would be defined by this delta X by L over here. Okay, and this shear strain will give rise to a restoring force over here, which would be parallel to this surface again. So that is F parallel. Okay, and this F parallel upon area would be defined as shear stress, you should realize. Okay, and the third way we can define is these stress or strain as bulk stress or bulk strain. So let's say there is a spherical body, and the pressure around it is P, and its volume is V. So if we change the pressure by, let's say, delta P, okay, if we change the pressure by delta P around it, so what will happen? Under the influence of this external pressure, it will get compressed, and its volume will become something like V minus delta V. Okay, so in that case, we can define bulk stress sigma V, you can say, and we can define bulk strain epsilon V. So bulk strain would be simply change in volume minus delta V upon V. Minus sign I have used because we can clearly see that delta V is negative. If we write V plus delta V over here, so delta V is a negative quantity. That is why we are using this sign over here. And in that case, like there would be a restoring pressure or restoring force per unit area experienced by it, and simply that will be equal to delta P over here. So that is how we define bulk stress and bulk strain. You should be aware of this thing, that it is a strain which is giving rise to stress. So what exactly we are doing the sequence, if you study that, if you apply some deforming force, okay, so and that deforming force will cause some strain, and due to that strain, okay, a stress will be developed in the material. So it is strain which causes stress and not the other way around. So being said that, let's try to solve one very simple question. Okay, let's say we have a uniform rod of, let's say, cross sectional area A, and we are trying to stretch it by using some perpendicular force F over here. Okay, so that is given in the question. And let's take one skewed cross section over here. Let's say skewed cross section which is skewed at an angle theta from the length of this rod over here. This is theta. Okay, and now here we are interested in finding out, like the question is find, let's say this section is AB. So find longitudinal and shear stress developed at section AB. Developed at section AB. So I hope that is simple question. So what we are gonna do, so first of all, we know that longitudinal stress is defined as perpendicular force upon area, and shear stress is defined as parallel force upon area. And we since we are looking at the section AB, so first we need to find out the area of section AB. Let's say that is A dash. So A dash, clearly you can see that is nothing but A upon sine theta over here. Okay, and this surface is experiencing a force in this direction. So let's say, let's resolve it into parallel and perpendicular components. So this component here would be perpendicular and this component here would be parallel. So clearly this angle is theta. So F parallel here is nothing but F cos theta, and F perpendicular is nothing but F sine theta, you should realize. And now we have just to substitute the value. So F perpendicular, that is F sine theta, and area is nothing but A dash is nothing but A by sine theta. So this will turn out to be this quantity, and this shear stress will turn out to be a parallel force, that would be F cos theta, and A dash, as we have found out, that would be simply A by sine theta over here. So this is longitudinal stress and this is shear stress developed at section AB, you should realize. So that is one of the important question. Okay, and there is one law which establishes a relationship between the strain and stress, and that law is basically named as Hooke's law. That is Hooke's law. Okay, and it says that for a small deformation, you should realize, okay, sigma is directly proportional to epsilon. Okay, so here what we can say, there would be some proportionality constant. So sigma is equal to, let's say, E time epsilon. So here this proportionality constant, that would be nothing but sigma upon epsilon, that would be known as modulus of elasticity. That is modulus of elasticity. And this modulus of elasticity is defined differently in different kind of situation. For example, in case of longitudinal stress and strain. Okay, so let's discuss about all these. For example, in case of longitudinal stress and strain. This modulus of elasticity would be defined as Young's modulus, and that would be nothing but longitudinal stress upon longitudinal strain over here. So rearranging that, like since sigma is, we know that is nothing but F by A, or F perpendicular by A, and epsilon is nothing but delta L by L. So you can say Young modulus would be defined as FL by A delta L. So this is for the longitudinal one. And for shear stress and strain, you must realize, so the modulus of rigidity, we say, the modulus of elasticity would be known as modulus of rigidity, and that would be nothing but sigma s by epsilon s over here. And as we have learned, okay, so sigma s is nothing but F parallel upon area, and this here would be nothing but x by L. And in this diagram, if you look the above diagram, I forgot to mention, like this quantity here will approximately be equal to tan theta also, where this angle is theta. Okay, so clearly, so this would be shear strain would be simply equal to tan theta, assuming theta is very, very small. This could be approximated as F parallel upon A theta also. Okay, and in case of bulk modulus or bulk, okay, we define something called bulk modulus, which is nothing but sigma v upon epsilon v. Okay, so here in other words you can write that would be delta p upon minus delta v by v. I am again pointing out to this quantity over here, delta v here is negative, so we are using a negative sign to make the denominator positive over here. So this is how bulk modulus is defined. Okay, so now let's take some questions in which we will be using these modulus of rigidity, okay, in order to find out the elongation, etc. So one very simple question let me put over here. So let's say we have a uniform ring of, say, a radius r, okay, and its density is rho, okay, and its Young's modulus is y, and this ring, let's say, is rotated about this axis with angular velocity omega. Okay, so due to this omega there would be elongative tension developed in this ring. Okay, and that will cause the length of this ring to increase, or radius of this ring to increase. Okay, so I want to find out the small increase in its radius. The question is, find small increase in radius of ring. Okay, so now you should realize, let's imagine this to be a very, very thin material, okay, thin ring of cross sectional area A, and let's say that is uniform. And what we are gonna do over here, something like this. So let's say, let's take a small element, okay, of this ring, okay, which subtends an angle d theta at the center. Okay, so this part of the ring, this element of the ring will experience T tension from this side and T tension from this side, and since this is undergoing rotation, so this will be experiencing a pseudo force that would be away from center. Okay, so that is, let's say, some pseudo force, and its magnitude you should realize that is going to be dm into omega square into r over here. And dm, you should realize, that is rho density is given, and volume here would be nothing but ADL. So cross sectional area, let's say, is A, and DL would be nothing but R d theta, and that multiplied with omega square R. So this would be something like this. Okay, and taking the force balance, the component of this force towards the center and component of this force toward the center, you should realize that is T sine d theta by 2. So the net component, the net force balance would be something like 2T sine d theta by 2 is equal to to this centrifugal force, which is rho a omega square r square d theta over here. So and also you should realize that this d theta by 2 is very, very small. So sine d theta by 2 can be approximated as simply d theta by 2, and that again gives rho a omega square r square d theta over here. So simply like T by A, you can say that is nothing but the sigma over here, and that would be simply equal to rho omega square r square, because you can see this d theta and this two terms will get cancelled. Okay, and you also know that this is nothing but uh, this is stress. So stress is nothing but epsilon times y. Okay, because y is defined as stress by strain. So here rearranging that, epsilon would be simply delta r by r, you can say. Okay, and that will be equal to or you could have written delta L by L, but delta L by L will be simply equal to delta R by R, because see, L is nothing but 2 pi R. So delta L by L, you can write it same as delta R by R over here. So delta R by R is going to be simply rho omega square R square upon Y over here. So delta R simply will be equal to rho omega square R cube upon Y. Okay, so clearly one thing you should notice, that delta R is directly proportional to R cube over here. So this was one thing. And let me introduce one more parameter in order to study elasticity, and that is called Poisson's ratio. Poisson's ratio. Okay, so Poisson's ratio, let's define it. Okay, for example, let's say we have a cylinder. Okay, and we have put some, let's say its length is L. Okay, and its diameter is D, and we deform it and try to put it under elongative stress. Okay, so it's definitely its length will increase. Its length will increase over here. So length will increase from L to L plus delta L. Okay, and its obviously its diameter will also change to some d plus delta d. So you should realize, if delta L is positive, then delta D got to be negative. If one dimension length is increasing, the another dimension will definitely be decreasing. Okay. So here we define something called Poisson's ratio, and its symbol I will be giving it as sigma. And it is defined as lateral strain upon longitudinal strain. Okay. So, for example, if we are applying force in this direction, some stress is in this direction if we are having. So that means along the length, it will be known as lateral strain. So this will be simply delta along the perpendicular to that direction, that would be known as lateral strain. So that would be simply delta d by d, and since delta d here we can see that is negative, so we can write it like this. So minus delta d by d would be lateral strain, and longitudinal strain, we have already seen its definition. This is going to be delta L by L. Okay, so you should realize here that is the above quantity, the denominator quantity is nothing but epsilon lateral. Okay, and this is nothing but E longitudinal. So you should realize this relationship. Like if you wish to find out E lateral, okay, so that would be simply sigma times E longitudinal. Okay, so if you somehow know the longitudinal stress, longitudinal strain, okay, so then you will be able to find out the lateral strain also if sigma is known to you. So one simple case I am going to discuss over here, like for example, for incompressible compressible material can we define or can we find out the value of sigma over here? So the idea is very, very simple. Incompressible material simply means that change in its volume, if it is deformed, okay, although its dimension will change, length and breadth, like its longitudinal, there would be some longitudinal strain, there would be some lateral strain, but delta V will be equal to 0, volume will not change. So you must realize, like for example, if we are taking a cylindrical material, so volume we can write it as pi d square by 4 into L over here. And if we take the relative change, so delta V by V will be simply equal to 2 times delta D by D plus delta L by L over here. Okay. So that simply gives us that minus delta D by D upon delta L by L will be equal to 1 by 2, or you can say 0.5. So for incompressible material, okay, the value of sigma, which is Poisson's ratio, that is lateral strain by longitudinal strain, that the value of sigma will turn out to be 0.5. One another interesting thing I want to discuss over here is you can relate between different moduli of elasticity. Okay, and here I am taking an example for the relation between Young's modulus and bulk modulus. You might be already aware of that relationship. This relationship is nothing but B is equal to Y upon 3 into 1 minus 2 sigma, where B is bulk modulus, Y is Young modulus, and sigma obviously is the Poisson's ratio over here. So how can we justify this relationship? Okay, so one simple model, let's take a cuboid. Let's take a cuboid here. Okay, and let's say its dimension, its length is x. Okay, and for example, this side is y, and or this side is y and this side is z, let's say, like we have taken it like this, and we have put some hydrostatic pressure or equal pressure from all around. Okay, like delta p is the pressure exerted from all the sides, you must realize. Okay, so under this pressure you must realize all its dimension, like for example, it's the value of x will decrease, the value of y will decrease, and the value of z, all these parameters will be decreasing, so its volume would be changing as well. Okay, so we want to have a relationship between b and y over here. So what we are gonna do, so let's say this is the delta pressure, delta P over here, the extra pressure that has been applied on this material. And let's try to find out the change in x. So let's say delta x by x we are willing to find out. So this is nothing but here delta x by x will be changing due to this pressure. So like for example, for an instant, let's say write it as delta px. Okay, so due to this pressure over here, okay, its length will decrease. So we can simply use y is equal to stress by strain formula. So stress is equal to, or strain is equal to stress upon y. So stress this side is having is you can say delta px. Okay, and that divided by Young's modulus over here. Why we are using this negative sign? Because the length is decreasing due to this delta px, because that is compressive in nature. And now this is delta py simultaneously. If we press this side over here, top and bottom, okay, so due to longitudinal direction would be along z axis. Okay, and with respect to that, the x axis would be the lateral direction, and we can use the above formula in order to find out that quantity, that E lateral would be sigma times E longitudinal. So that will be simply sigma times E longitudinal, and E longitudinal would be nothing but delta Py upon y over here. Similarly, we will be exerting pressure from this side. So delta Pz we can say from these two ends. So again, with respect to this force, okay, this direction, x direction, would be lateral direction. So here we can write sigma into delta pz upon y over here. But also you should realize that delta px, delta py, and delta pz are one and same thing, and let's say that is equal to delta p. So this will simply give us delta p by y. You can take common, and that would be, in bracket you will be having 2 sigma minus 1. Similarly, this is for example delta x by x. So similarly, delta y by y also you will be getting delta p by y into 2 sigma minus 1. And similarly for delta z by z also, that would be delta p by y into 2 sigma minus 1. And now you realize, like for example, we were looking for change in volume, delta V by V. So that would be nothing but V, you should realize, is nothing but X into Y into Z. So delta V by V would be nothing but delta X by X plus delta Y by Y plus delta Z by Z over here. So this will simply give us like the sum of these three quantities. So this is gonna give us 3 times delta P by Y into 2 sigma minus 1 over here. And delta V by V, you should realize from the definition of bulk modulus, that is nothing but minus delta P by B over here. So that is equal to, and you can take a negative sign common here, so that negative gets cancelled. So minus 3 times delta P by Y, and this will turn out to be 1 minus 2 sigma over here, and this delta P and this delta P will get cancelled. This negative sign will also get cancelled, and you will be left up with this expression B is equal to Y upon 3 into 1 minus 2 sigma. So, and similarly, you can derive relationships between other moduli of elasticity. This was one of the example. Okay, and now let's move on to the next thing here, and that is we are going to discuss strain energy. Strain energy. Okay, so like when a body is deformed, okay, from its stable equilibrium position, basically some work is being done on that. So that energy is stored, okay, inside the material in form of some potential energy. So this situation can be taken very similar to the situation of an ideal spring. Let's say for example, if you have a wire of, let's say, length L, and you elongate it by some length delta L, so a restoring force will uh, act in this direction, and we have learned to write the expression for this force, and that is nothing but YA delta L by L over here. If we compare this situation with an ideal spring, okay, so let's say this is a spring of spring constant K, and if we exert some force, and let's say its elongation is x from its natural length, okay, so it will experience, the spring will exert a restoring force, and that will be given by F is equal to Kx. So now comparing these two equation, okay, these two parts are elongations, so these basically are the proportionality constant, and we can compare, and we can very safely say that for example, if we take uh, this wire over here which behaves like a spring, means it obeys Hooke's law, then the effective spring constant of this wire would be simply K is equal to YA by L over here. So in that case, the strain energy which we used to write in spring, that was equal to half kx square. In that case, that would be half k into x square we will be writing over here. So the value of k is nothing but YA by L, and the elongation you can see, that is delta L square over here. So that is the strain energy, or you can simply say delta U. And one interesting thing you should notice, like for example, if both left hand side and right hand side, if you divide it by volume, for example A times delta L, then delta U by delta V will turn out to be, like for example A times delta L, if you divide, so what you will be getting, this A will get cancelled and you will be getting half into Y into delta L by L square, so which is nothing but half into Y into epsilon square. So what you can say, that strain energy per unit volume, or you can say energy density also, that is equal to half Y into epsilon square, or it can alternatively be written as, if epsilon you write it in terms of sigma and Y, so this will turn out to be sigma square upon 2Y, or also it can be written as half into sigma into epsilon. Okay, so these are the relationships for the strain energy stored inside the material due to the deformation caused by the external force over here. Okay, so according to the situation, whenever required, you can use any of these forms. Okay, so now let's try to look into some problems over here. So the first problem I'm going to take is elongation of a hanging rod due to its own weight, due to its own weight. Okay, so imagine like there is a rigid ceiling and we have a rod of the parameter, let's say that is given as rho is its density, A is its uniform cross sectional area, and Y is its Young modulus. Okay, okay, so now you should realize over here, like this is hanging under its own weight. So the tension in this rod will be varying with respect to height. So if we take a position which is at height y from the bottom, and if we take an element of width dy over here, okay, so this element would be under elongative stress or tensile stress, you can say. So there would be, you can say, F acting in this direction and F plus dF acting in this direction. So when you will be doing the force balance, the net force would be dF in, or the resultant of this and this would be dF in upward direction, and that will be balanced by its weight in downward direction. So you should realize that this dF is nothing but equal to dm times g over here, and dm is nothing but density is given, so rho times volume of this element, and that is nothing but a dy into g. Okay, so this df we have got, and if we integrate this term rho a g into dy with proper limits, what we will be getting, like for example at y is equal to 0, at this point the tension would be nothing but 0 over here, or the force will be nothing but 0, and you can say as a function of y we are willing to find out, so this would be f over here, and rearranging this simply, this f will be nothing but rho a g times y, and you can say f by a, which would be sigma, would be nothing but rho gy over here. So that is the simple thing. So once sigma is known to you, it is very easy for us to find out the elongation in this element. So elongation in this element, let's say, is dl, and that would be equal to sigma by y times the length of this element, and the length of this element is nothing but dy over here. Okay, and we can integrate both sides, okay, to get the total elongation. For example, the left hand side would be delta L, okay, and sigma as a function of y we have already got, so that is rho gy upon y into dy, and that we need to integrate from 0 to say L. Okay, so this will give us simply rho gl square by 2y over here. So that is the total elongation. And let's say we are also interested in finding out the strain energy also. So let's try to find out the strain energy stored. Strain energy or say delta U. So delta U would be simply, let's use this formula which we have written over here. This would be the most appropriate way of having that. So potential energy per unit volume or strain energy per unit volume was nothing but sigma square upon 2y, and that multiplied with dV will give the energy stored in this elemental volume. Okay, and when we will be integrating over initial to final value, we will be getting the total strain energy stored. Okay, so now let's be substituting all the values. The value of sigma we already know, so that would be nothing but, so rho square g square y square upon 2y, and dv obviously is nothing but a times dy over here, and we need to integrate it from 0 to L. Okay, and that will be giving you rho square g square al cube upon 6y over here. Okay, so that's the idea. One thing we can do over here, let's say for example, right now it is hanging under its own weight. Okay, and if we at the same time start pulling this with some external force F over here, okay, so in that case this limit here will change. Like for example, here it was at y is equal to 0, so this will become F over here. So in that case, sigma will become rho gy plus F by A over here. So in that case, this delta L terms will become FL by AY, an additional term over here, and here one additional term will be there as well. So sigma square upon 2y, so you can say F square by A square, okay, upon 2y, so that is 1 upon 2y, okay, and that multiplied with the total volume A into L. So this would be an additional term, okay, if this additional force is applied at one of the ends. So that is one situation. Let's be looking at another situation, another interesting case. So let's take the case of rotating rod. Let's say we have a uniform rod, that is rod of uniform cross section. Okay, let's say the cross sectional area is A and its length is L. Okay, and its density is rho and its Young's modulus is y over here. These parameters are given, and this rod is being rotated with angular velocity omega over here, and we want to find out like what would be the elongation in this rod. So in order to do that, so we first need to write the force profile or tension profile. You must realize, so you can say at a distance of x, let's choose an element of width dx. So like this element will be under tensile stress. Okay, so let's say the tension this side is T, so the tension this side would be T plus dt over here. Okay, and apart from that, and another force you can imagine, because it is in rotating frame of reference, that would be acting away from center, that would be dm into omega square x over here, and the net force acting on this would become dt plus dm omega square x. uh, that would be the net force, and for the equilibrium of this, that will be equal to 0 over here, you should realize. So when we will be rearranging this equation, dt will be equal to, and dm obviously you can write, that is rho a dx into omega square x, and there would be a minus sign over here. So this would be the relationship. Now we must integrate both sides, okay, with appropriate limits in order to get the tension as function of x. So you should realize that at x is equal to L, means at this end over here, the tension is going to be equal to 0, and we are willing to find out at x is equal to x what would be the tensions. Okay, so T will be simply equal to, by solving this, you will be getting rho a omega square by 2 into L square minus x square over here, and that is a simple integration. And T by A, so this will be basically giving a sigma, so that is rho omega square by 2 into L square minus x square over here. So once sigma is known to us, it is very easy for us to find out either elongation or a strain energy. So in that case, elongation here, elongation delta L will be simply equal to, that would be sigma upon upon y into dx integral of that from 0 to L. And when we will be substituting the value of sigma over here, okay, what we will be getting is rho omega square upon 2y, you can say, and that would be L square minus x square times dx, and we need to integrate it from 0 to L, which we will be getting it as rho omega square L cube upon 3y over here. And similarly, when we are required to find out the strain energy delta U, we are going to use the formula sigma square upon 2y into dV. Okay, so you should realize by this time that finding out sigma, if it is variable, so as a function of x over here, and that will give us, if sigma we are able to find out, this integration will give us elongation, and this integration will simply give us the strain energy stored. So all uh, uh, the thing that will be left only is the calculation. The calculation here, when you will be substituting the value of sigma as this quantity over here, which we have already found, you will be getting 1 by 15 rho square a omega to the power 4 into L to the power 5 upon y over here. So that is how you can do. So that is the case of a rotating rod. And now let's move on to some other cases here. And that case, let's say, the case of accelerating rod. Okay, the case of accelerating rod. So let's say there is a uniform rod of a density rho. Okay, and its cross sectional area is A. Okay, and its length is L, and Young's modulus is Y over here. Okay, so these parameters are given, and apart from that, let's say we are pulling the both the ends with some forces. Let's say this force is F1 and this force is F2. So you should realize this rod is under elongative stress. Okay, so you must first find out, if you are required to find out the elongation and strain energy in this rod. Okay, so what we are first required to find out is the force as function of the distance from any of the end, you can say. Like a force would be variable, or stress experienced by any cross section would be a variable. So our first job would be to find out that quantity. So let's do that. Okay, so at a distance x over here, let's take an element of width dx. Okay, so this element will be under elongative stress, so this would be f, and this would be f plus df. Okay, so clearly, now you should realize this df will be the net force experienced by this element, and that will be equal to mass times acceleration. And mass of this element is going to be, let's say its mass is given, let's say m. So its mass is, mass per unit length would be m by L into dx over here. So that is dm. And its acceleration, obviously, if we assume that f2 is greater than f1, so that would be simply f2 minus f1 divided by m over here. So this basically is nothing but f2 minus f1 upon L into x, or into dx over here. So that is df. Okay, and if we integrate it with the proper value over here, let's say for example at x is equal to 0, the value of f is nothing but f1, and we are trying to find out the value of f as function of x. So this simply will give us f is equal to f1 plus f2 minus f1 upon L into x over here. So once we have got the velocity or force profile over here, the finding out the elongation delta L simply will be equal to sigma upon y into dx. So let's directly write that. So 0 to L we have to integrate, and that would be 1 by ay multiplied with the force over here. So that the force already we have got it as f1 plus f2 minus f1 upon L into x, and that into dx. So this will simply give us like f1 plus f2 by 2 into L upon AY, and if you look closely, this is nothing but this would be the average force. So you can say F average into L upon AY simply. Okay, so this is the elongation, and similarly you can find out the strain energy also. By that time you might be have got comfortable with that, so that would be delta. You would be formula you already know, no? 0 to L sigma square upon 2y into dv, etc., and you just have to put the value of sigma as f upon a, and after substituting everything, like, you will be getting 1 by 2ya over here, and that would be, in this you will be having f1 plus f2 minus f1 upon l into x. Okay, and this is square we will be using into dx, and ultimately after solving for everything you will be getting 1 by 6ay, and in the bracket you will be having f1 cube minus f2 cube upon f1 minus f2 over here. So this is the case of accelerating rod. One another interesting case we can take, like for example, this is this uh, uh, becomes confusing for some students. So that is why I am discussing this point over here. So let's say F1 here is in this direction and F2 here is in this direction. Now, previously we were stretching from both the sides. So here now what we are having is we are compressing it from one side and trying to stretch it from the other side. So will we be able to find out the elongation in this case and strain energy as well? So in order to find out the elongation, we are gonna use the same method. So let's say at a distance of x we take a small element dx. Okay, and for example, this element, for instance, let's assume it is under elongative stress, so like this direction I have shown. Okay, so f plus df you should realize. Okay, and if the value of f turns out to be negative, we will be saying that it was not elongative but compressive stress. Okay, but let's find out f as function of x. Okay, so the df, simply we can write df will be equal to mass times acceleration of this element. So mass of this element would be m by l times dx, and its acceleration would be definitely f1 plus f2 by m. Okay, so this would be the df, and when we will be integrating over here, you should realize, let's look very carefully how to put the limits over here. So at x is equal to 0, what is the value of force? What would be the value of force? So here we are saying that it is elongative stress f we have defined, but here at x is equal to 0, this f1 is compressing it. So here I must put the value of f, initial value at x is equal to 0, as minus f1, because the positive a sign of f we have taken for elongative stress, and at x is equal to 0 and f is equal to f1 is a compressive stress, so we have assigned a minus sign over here, and we are willing to find out f as function of x, so that is the upper limit. So this will simply give us f is equal to f1 plus f2 into x by l minus f1. Okay, so looking at this relationship over here, like, can we find out a point of no stress? Can we find out a point of no stress over here? So obviously point of no stress simply means where f will be equal to 0. So when you will be equating this, okay, so simply x you will be getting it as f1 divided by f1 plus f2 into l. Like for example, from this end it would be this much, from the other end it would be f2 times l divided by f1 plus f2, obviously. So what we are basically seeing, that if we draw the force profile, imagine this is the rod of length l, and this end is experiencing a force f1, and we are drawing it like this way, and this end is experiencing a force f2 over here. So in this relationship you can clearly see that the force is varying linearly with respect to x. So that is how the force profile will look like the force will be decreasing, like here in this direction, here in this direction. So this part of the rod here would be under uh, you can say compressive stress or compression, and this part will be under elongative stress, or that would be basically elongation. Okay, and this part here you should realize would be a point of no stress, the value of which we have already found out. Let's say for example, this is, sorry, this was f1 I have written, and this is f2. So this is l1 and this is l2 over here. Okay, so this is the idea. Okay, obviously the value of L1 and L2 we can find out. And being said that once we have got the force as function of x, we can find out the elongation delta L also, and the elongation here would be nothing but again sigma upon 2y, or sigma upon y into dx. So sigma here is nothing but this relationship we will be using, f1 plus f2 into x by L minus f1 by a. So let's take 1 by ay outside the integration sign, and this term dx we should integrate it from 0 to L, and what you will be getting simply is nothing but L by ay into you can say f2 minus f1 by 2 over here. And you should realize also, okay, in this situation, since we have got this relationship, if f1 is equal to f2, so that means the net elongation in this rod will be equal to 0. So that does not mean that any part of the any element of the rod has not been elongated. The idea is simply the one half of the rod will be under compression, and another half of the rod will be under elongation. So whatever is the compression in the one half, same will be the magnitude of elongation in the other half. So net elongation will be equal to 0 in that case. And also strain energy you can find out, and then I'm not going to do calculation over here. Just try to solve it by yourself, and the answer you are likely to get is 1 by 6 ay. Okay, and that would be f1 cube plus f2 cube, and that divided by f1 plus f2. You have seen the calculation, the type of calculation in the previous question also. Okay, and one since we have got only one lecture and we have been discussing only about the Young's modulus also, let's try to do a few things about bulk modulus also. So one thing I will be taking here is the variation in density, due to bulk strain. Okay, and one important thing I will be taking here, let's say, for example, there is some material whose density is rho. So obviously rho is defined upon mass upon its volume over here. And if we put it under some strain or bulk strain, its density will be changing, like rho dash can be written as mass will not change, and let's say volume is changing to v plus delta v over here. So this is the expression, and if we write rho dash by rho over here, so this will simply give us v upon v plus delta v, and rearranging that you can write it as 1 plus delta v by v here. Okay, and from the definition of bulk modulus you are aware about this quantity. This is simply going to be 1 upon 1 minus delta p by b. So what we have got here is rho dash is equal to rho upon 1 minus delta p by b over here. Okay, and I am now going to introduce one very special case, like for example, for solids. For solids, you realize that the solids compressibility is very small. It is very difficult to compress, so its bulk modulus is going to be very large. Okay, so that is why we can say this delta p by b would be a very small quantity in comparison to 1 over here. So over this denominator we can use binomial approximation, and only for solids rho dash I will be able to write it as, using binomial approximation, rho into 1 plus delta P by B. Okay, so please try to understand this formula you can use anywhere, but if you are using this formula, that would be applicable only when this delta P by B term is very small in comparison to 1. Okay, and that will be mostly for solids. So that is one point I wanted to discuss. And one another aspect of the theory of this elasticity chapter is the very important point I'm going to discuss over here is a stress strain curve for a metal wire. Okay, so let's draw a stress strain curve, that is, say, sigma upon epsilon. Means if we are putting some strain in the in a metal wire and we are checking for the stress developed in it, okay, and plotting the graph, and this graph will look something like this. Okay, up to some point it will vary linearly, and then it will go like this. Would be the nature of graph, something like this. Okay, so let's define different points. So let's say this is 0 or O, and this is A. Okay, and there is some point B over here, and let's say there is some point C over here, and there is some point D over here, and this is point E. So let's try to understand the point each by uh, uh, understand each point one by one. So A is basically known as proportionality limit, proportional or simply proportional limit over here. So why we are saying it proportional limit from O to A, sigma, like you can see the graph is a straight line passing through origin. So sigma is directly proportional to epsilon, or you can say Hooke's law will be obeyed till proportional limit A only. So that is what the proportional limit A is. Now let's look at point B over here. Point B is known as elastic limit. Point B is known as elastic limit. Means, like for example, if we stretch the wire till point B, if we stretch the wire till point B, you should realize and remove the external deforming force. Okay, the wire will regain its shape completely. So that is what we are saying, that elastic limit. Up till point B, this material is behaving like a perfectly elastic material, because when we are removing that external deforming force, it is completely regaining its shape. C is some point known as yield point, and about yield point C, I must say yield point C is a point at which permanent deformation of 0.2% remains in the wire when deforming load is removed. Like for example, when deforming load is removed, it will follow this path and some permanent deformation will be left up with, and that would be nothing but 0.2%. Okay, so that is what yield point is. Okay, and now you should realize that even if we keep on stretching that material, generating some strain, okay, so you should realize stress of here you can see that the stress increases till point D. Okay, and point D you can say, just wait for a while, I think like my pen got hanged. So point D corresponds to the maximum stress over here, or that is also known as ultimate tensile strength. Okay, sigma U is nothing but ultimate tensile strength, you can say. So you can see that up till point D, okay, when you increase strain, stress would be increasing as well. But beyond that point, you can see if strain is increased beyond point D, stress start decreasing. Okay, beyond that point D, when you are increasing the strain, you can see the stress is decreasing over here. And beyond that point D, also you must realize the necking start. Necking means like the wire was previously like this and it was elongated, and necking means it will start forming a neck. Okay, so its cross sectional area at this, like any some point, it will start decreasing, and ultimately if you keep on increasing the strain, okay, ultimately it will fracture or it will break at point E. So E is basically fracture point. Okay, so this we have looked at a general stress strain curve for a metal wire. Obviously, you can draw stress strain curve for different type of material. So this graph will be different as well. So here, like our time is up. Okay, already. So that's it for now. So goodbye. Thank you for joining.